This is a demonstration of the ambiguous triangle case and the law of sines. Let's start out with angle A equaling 30 degrees, side length A equaling 4, and side B equaling 10. When you start out with one of these problems, the first thing you want to do is draw a little diagram. And I find that the best way to start this process is with one leg of the triangle being horizontal, one side coming up at our 30-degree angle, and this lower side is going to be side C, which is unknown. The other side that's visible here is going to be side B, which is 10. And we don't know exactly where side A is going to be. It could be in here, could be in here, could be straight down. It might be long enough that it reaches the horizontal leg. It might not actually be long enough. We're going to find out. So the first thing we need to determine in order to decide where side A goes, or where it aims, or however you want to say that, is determine this distance h. The analogy I like to use is that this horizontal leg is the ground and that this angled side is a ramp. And so h is describing the distance from the end of the ramp down to the ground. To determine h, I'm going to actually take that distance h, which is vertical, put it right in here, and create myself a right triangle. And I'm going to use the sine function and say that the sine of 30 degrees, our angle A, I could put the A in over here. The sine of 30 degrees, which is equal to opposite over hypotenuse, is going to equal lowercase h divided by our hypotenuse on that triangle, which is 10. Multiply both sides by 10. We have 10 times the sine of 30 degrees is equal to h. The sine of 30 degrees is equal to 1/2. So h is 5. Following with my analogy, that means that the height of the ramp above the ground is 5 units. Or we could say 5 feet. Knowing that, if I look at side length A, which was given to us as being 4, I know that we've got a problem, especially as far as the analogy is concerned. It means that if we were to drop a rope of length 4 off the end of our ramp up here, our rope is going to come down only to about there. It's not going to reach the ground. In other words, we have no triangle. Now, if we were to back up and change side length of 4, let's go in and erase the 4 and change it to a 5. Let's make that another color. Let's make this a 5. Side length A had been given to us as a 5. Then, the h that we were talking about, when we draw that in, means that the rope hanging off the end of the ramp coming down would touch the ground perfectly. It fits right in there. It meets the ground at a right angle, and it means that we have one triangle. So a single solution to this problem occurs when the length of the rope, which is our A value, across from the given angle measure, is equal to our h value, the height of the ramp above the ground. So far we've seen one possibility where the rope is not long enough to reach the ground. In other words, A is less than h. Another possibility is that A is equal to h. And now we need to cover the last two possibilities. Which are two triangles and another scenario where we run into one triangle. If we continue with the analogy of a rope, I'm going to do some more erasing here. We know that our h value is 5. I'll leave that on the screen. Let's look at if we had a rope that had a length of 10. If my rope had a length of 10, I could pull that rope underneath my ramp and have it come from the end of my ramp all the way back into this vertex in here, which wouldn't make for much of a triangle. I would have my rope and my ramp would be basically laying right on top of one another. This 30-degree angle wouldn't mean much. So a rope length of 10 would maybe suggest it would be a better idea if I pulled the rope out and away from my angle, creating this one pretty wide triangle, obtuse triangle. That's with a rope length of 10. Let's look at a rope length that's even longer than that. Let's go to a rope length of 15. With a rope length of 15, oh boy, erasing too much there. With a rope length of 15, the rope would have to be pulled way out here. And side C would then be much longer. Very obtuse triangle. There's no way that we could pull a rope that has a length of 15 under the ramp because the rope would have this kind of sag to it. That definitely does not make a triangle. So in the case where our A value is longer than the H value, in other words, it reaches the ground, remember that this is the rope, and our rope is longer than the ramp, this tells us that we have only one triangle. And we're going to talk in a moment about how we would then find out this angle measure, and determine side length C. And we're going to hear about that process as we address our last scenario, which is the scenario where we have two triangles. Let's get into that one. All right, let's take some of this out too. There we go. I think I'm going to start my diagram over just so that we can draw it a little bit larger because we're going to be putting two triangles on the same diagram. So let's have our horizontal part of our triangle there. Let's come up here with the ramp. We've got our angle measure of 30 degrees in here. Little degree symbol there. That's A. This is side C. This is B over here, which is 10. And the two possibilities are that we're going to have our rope coming in here, or perhaps our rope is going to come out here. And how do I know to consider this possibility? Two triangles, if the rope length is longer than the height that we talked about earlier. It's 5 in this particular example. If the rope length is longer than the height, but the length of the rope is shorter than the ramp. In this case, we have, well, I need to give you a new rope length that satisfies these conditions. So let me come up here and erase the 15 that I had as my A value, and let's use an A value of 7. Let's put the 7 in red to highlight that we've made that change for our last example here. That's now a 7. Our ramp length is still 10, so we see that we're satisfying this condition. This is how we know we have two triangles. The first triangle that we're going to address is this larger one that starts at A, comes up the ramp, goes out away from the ramp, and then comes back in. So I'm going to redraw that triangle, especially because that did not cover that existing diagram very well. All right, here we go. This is going to be side length A, which I said is 7. This is still 30 degrees. This is still 10. This is angle B. This is side length C and angle C. There's a reason why I'm addressing this triangle first, and it's because the size of this angle is going to be given to us by using the inverse sine function. And if I were to draw this triangle first and look for this as angle B, the inverse sine function would not return an appropriate angle measure. So now with this as our triangle, we see that we have what I like to call a pair. Both of my A values are there, capital A and lowercase a, the angle measure and corresponding side length. Here, for my B values, I have half of a pair, which means I have enough information to fill in 3/4 of the law of sines. The law of sines says, now I'm solving for angle B, so I'm going to write that the sine of angle B, putting that in the numerator, over lowercase b is equal to, remember the full pair here was of the A values, so I'll write that the sine of capital A divided by A is the other half of the equation. Let's fill in the blanks here. We don't know what the B value is, that's what we're solving for, so I'm going to leave the capital B there. Over lowercase b, that's our ramp length of 10. This is equal to the sine of capital A, which is 30 degrees, divided by lowercase a, our rope length of 7. Let's solve for the sine of B, so I'm going to multiply both sides of my equation by 10. That allows me to cancel out my 10s over here. Now the sine of B is equal to 10 times the sine of 30 degrees. Let's go ahead and evaluate that. Excuse me. Sine of 30, we already mentioned, is equal to 1/2. We're dividing that by 7. And now we have that the sine of B is equal to 5/7. In order to find angle B, I'm going to take the inverse sine of both sides of my equation. That sine looks like sine to the -1, but we say inverse sine. That cancels out the sine on the left-hand side and says that we now have to take the inverse sine of 5/7. You'll need, at the very least, a scientific calculator in order to do this. Using our scientific calculator, we find that the inverse sine of 5/7 is 45.58 degrees. This is approximate. I've rounded it to the second decimal place there. It's actually 0.5846914. We don't need that much accuracy, although I guess it depends on the call of the question. This is part of our solution, and if we go back and look at our diagram, if you wanted to, you could fill in that angle measure right here. That's angle B. Now we've got another pair, which is nice, but it also means that we can find the measure of angle C by taking 180 degrees, subtracting the 45.58 as angle B, and subtracting the original 30 degrees from angle A, and we find that our C value is 104 degrees. Let's even say 0.42 rounded. All right, so that's angle C. And we could go back and fill in angle C in our diagram. And now that I have that angle, it means that I have a half of a pair here, with this being the 104.41. And I can solve for side C, again using the law of sines. And so this is a half of a pair. The C is here. I would go back and use the A's as my full pair because these are nice whole numbers and you don't have to use any recalled or stored long decimal places like we had for angle B. All right, now let's talk again about the second triangle. In our diagram, there was the possibility of having this rope come in under the ramp like this. Let me draw that one more time, have it come in a little more steeply. There we go. And remember that the length of this rope is 7, whether you pull it out away from the ramp or you pull it in underneath the ramp, which means that this triangle is an isosceles triangle. And since these two side lengths are the same, their opposite angles are going to be the same as one another. Since this angle in here was our original angle B, which I'm going to call B1 at the moment, that was 45.58 degrees. That means that this angle, my eraser likes to turn on all by itself, so I keep erasing side lengths unintentionally. This angle measure is also 45.58 degrees. Since this angle, because of our isosceles triangle, is also 45.58 degrees, it means that this angle is 180 minus 45.58 degrees. I'm going to call that angle B2, and it will appear in our next diagram, 180 degrees. I'm just doing these calculations as long as we're here and talking about it, and I'll refine the diagram in a moment. That angle measure is 134.42 degrees rounded to 2 decimal places. All right, that is angle B2. You could come back up here and use this diagram and let go of the right-hand side of it so that we're just focused on this triangle here. In fact, let me see if I can do that somewhat gracefully without having to redraw the whole thing. Let's get rid of these, and this, and the 7, and I'm probably going to have to redraw that. Yep, we'll just save a little bit of space here. Let's close our triangle back up. This is the angle that I was calling B2. Angle A has not changed. Side length B has not changed. This is still our ramp length of 10. Our rope length is still 7, so I'll leave that there. This angle measure, however, we just determined is 134.42 degrees. This angle, the original angle A, is still 30 degrees, which means that angle C up here in the top right can be found the same way we found it in the last triangle, which is subtraction from 180. I've got 180 minus angle A at 30 degrees minus the new angle B2, which is 134.42 degrees. And jump into the calculator. We could call this C2 since it's part of our second triangle. It's the second angle C that we've seen so far in this very long triangular conversation. I got 15.58 degrees rounded to 2 decimal places. And that's angle C, and side length C can be found same as when we talked about our first triangle. This makes a half of a pair. Since we know angle C now is the 15.58 degrees, what we don't know is side C, and we can use angle A and side A as the full pair in order to do the law of sines again to find side C. This is a crazy scenario, all of these triangles, but with a little bit of practice, you should be able to get pretty good at this. I would say that some of the key factors to solving this problem are, first of all, determining whether or not you are actually in the two triangle scenario. That's going to only happen if you are in a side-side angle situation where the angle measure that's given to you is acute, less than 90 degrees. Again, I recommend that when you draw your diagram that you, well, first of all, if you're in side-side angle and you have an acute angle measure that's been given to you, then you've got the possibility of two triangles. What should you do next? The next thing you should do, you're writing this down, you're making a to-do list. This is the process that you need to remember to solve this problem successfully. You've got side-side angle, you've got the acute angle. It's now time to determine if you've got two triangles. Next thing you need to do is calculate H. Then you need to make this comparison. Your height compared to your rope length compared to your ramp length. If this relationship exists, then you definitely are going to have two triangles. From there, you need to move to the triangle where you have the rope pulled out away from the ramp, because the next thing you're going to find once you've got that diagram is the B value. I wasn't calling it B1 when we talked about it originally, but I would call it B1 if I were you. You're going to solve for B1 first because the inverse sine function has a range of output values that are between negative and positive 90 degrees, which means you're going to be getting this angle measure right here, which would not fit or make any sense in this diagram. So it's a good thing we started with the rope pulled out away from the ramp. Once you've got that B value, fill it into your diagram up here, and now you can continue to find angle C using subtraction, and then side C using the law of sines again. From there, oops, I went too far. You can draw your second triangle with the rope pulled in. Oh, that was the eraser. With the rope pulled in underneath the ramp. There it is. You're using subtraction combined with your isosceles triangle part of the conversation that we had. I won't redraw that diagram in order to find B2. Once you've got B2, you're doing subtraction to find angle C. We saw that arithmetic here. And from there, you're using the law of sines again in order to find side C. I hope that all these different colors and different scribblings in my mediocre handwriting have been helpful. Best of luck to you with the law of sines and the ambiguous triangle.